Welcome to Enigma Universe, a channel dedicated to unraveling the mysteries and wonders of the cosmos. In this episode, we embark on a journey into the captivating universe of metamaterials, where science and imagination converge to push the boundaries of what's possible. Friedrich Nietzsche used his words, that you stare into the abyss stares back at you, take on new meaning as we delve into the realm of metamaterials, substances that defy nature's limitations to usher in a new era of possibilities. Metamaterials are extraordinary creations engineered to exhibit properties that challenge the norm in the world of materials science. They possess the unique ability to manipulate light waves, sound waves, and electromagnetic properties on a grand scale. In this episode, we'll focus primarily on electromagnetic and acoustic metamaterials, which have already demonstrated their potential to shape our future. But what makes metamaterials so unique? It all comes down to their permeability, permittivity, and index of refraction, which dictate how they interact with electric and magnetic fields, as well as how they bend and reflect light. Most materials have positive values for these properties, but metamaterials stand out with their dual negativity, negative permeability and negative permittivity. Now let's dive deeper into the fascinating world of metamaterials and explore how they can manipulate the electromagnetic spectrum, extending beyond and the world of materials and physics. Friedrich Nietzsche's profound words, if you stare into the abyss stares back at you. Take on a new meaning when we delve into the realm of metamaterials. These extraordinary substances have the unique ability to electrify desires, yielding results as diverse as the concepts behind them. Today, we embark on a journey into the captivating universe of metamaterials, which often defy nature's limitations to usher in a new era of possibilities. The term metamaterial is often used to describe any material engineered to possess properties not naturally found in our world. Yet, if we scrutinize this definition, it encompasses nearly every material we've developed throughout history, from the earliest days of the Bronze Age to the present. Most metals, for instance, are scarcely encountered in their pure form in nature, and alloys like bronze are even more scarce. We can extend this point further to encompass various materials like glass, which, though found in nature, are fabricated with distinct properties. The world of materials we have at our disposal today primarily consists of substances painstakingly crafted from the ground up. However, in our quest to explore metamaterials, we must narrow this all-encompassing definition. What characterizes most metamaterials is their exceptional capacity to manipulate light and sound waves, along with electromagnetic properties on a grand scale. In this context, let's redefine our focus on the electromagnetic and acoustic properties of metamaterials. These fields are the most comprehensible, having already initiated remarkable changes in our environment. Although the realm of advanced materials harbors numerous theoretical applications, this part will predominantly concentrate on electromagnetic and acoustic metamaterials, which have already demonstrated the potential to shape our future. While we may discuss more esoteric concepts such as using computronium, neutron, or utility fogging future texts, for now, we will venture into the realms of electromagnetic and acoustic metamaterials, whether interest or erotic. To delve deeper into the physics of these materials would be an intricate task, but it primarily revolves around their permeability, permittivity, and index of refraction. These characteristics dictate how materials react to electric and magnetic fields, as well as how they interact with light. Most materials exhibit positive values for these properties, but metamaterials boast the unique quality of a dual negativity, negative permeability and negative permittivity. The focus of our discussion, though, is the electromagnetic spectrum. While we often refer to light, the concept extends beyond the visible spectrum and encompasses infrared, microwaves, and radio waves. To grasp the idea of a negative refractive index, picture a vertical mirror reflecting a beam of light from a high angle. Metamaterials are intriguing creations that challenge the boundaries of what's possible in the world of materials science. These remarkable substances are needed to exhibit properties that do not occur in nature. While this definition could include many materials that humans have crafted over the millennia, we'll narrow our focus to the kinds of metamaterials that can manipulate light waves, sound waves, and electromagnetic properties on a larger scale. Metamaterials are known for their ability to influence the way light and other electromagnetic waves interact with them. These effects are driven by the material's permeability and permittivity properties, which also influence its refractive index, how it bends or reflects light. For the sake of simplicity, we'll mainly discuss visible light, but these principles apply to other types of electromagnetic waves, from microwaves to radio waves. To understand this better, picture a vertical mirror. When you shine a beam of light onto it from a high angle, the light hits the mirror and reflects off in the opposite direction, like a mirror should. Now, imagine replacing this mirror with a horizontal metamaterial. The fascinating thing is that this metamaterial doesn't need to be an actual mirror. It's a material that can simultaneously refract light beams. It's as if you have millions of vertical mirrors within the material, working in harmony to manipulate light. This effect, called negative index of refraction, is quite different from what we observe in typical materials like water, which merely bends light inward. But how are metamaterials created? The process involves constructing geometric patterns using materials with negative permeability and negative permittivity. These materials are organized in repeating patterns called cells, with each cell being smaller than the wavelength of the light it affects. At a larger scale, the combination of these materials results in a substance with a negative refractive index. To help illustrate this, consider your leaf computer monitor screen. Even though it's not a metamaterial, your screen comprises numerous pixels, each consisting of red, green, and blue lead elements. By activating or deactivating these elements, your monitor can generate a vast array of colors and brightness levels. When you zoom out, you see the video you're currently watching, yet you're unaware of the specific hues and brightness levels of individual pixels or the lead elements within them. All you care about is the overall image and our magic of moving pictures. In a similar way, metamaterials consist of individual elements that, when combined, create properties that defy the norm. In metamaterials, the interactions of individual elements differ markedly from those in conventional materials. These individual elements, often referred to as cells, must be assembled into geometric shapes, which are smaller than the wavelength that the specific form of radiation or sound the metamaterial is designed to manipulate. Historically, metamaterials were primarily developed to influence the radio spectrum and sound waves due to the relatively easy task of creating elements that could interact with the longer wavelengths of radio and sound. Microwaves, which are the shortest radio wavelengths, measure around a millimeter or more, making them over 7,000 times larger than even the young-forward wavelength, which is about 1,400 nanometers. In the next part, we'll take a closer look at the creation of metamaterials and their interactions of various forms of radiation and sound. This process allows these materials to achieve a negative refractive index, defying the behavior of conventional substances. So stay tuned as we delve deeper into the metamaterial universe in part 2 of our exploration. Don't miss the opportunity to unlock the secrets of these extraordinary substances and their potential to revolutionize our understanding of science and technology.